Hello guys, welcome to the tutorial in which we will be understanding couple of examples of f divergence and then the properties of f divergences mathematically. So now let us in our lecture section Professor Pratosh sir would have defined f divergence. I will redefine it and then we will prove all those properties and then we will take couple of examples and then we will say that we will mathematically prove that why the KL divergence which is there is not a distance metric. Okay. Now this is the overview of what we shall be doing in this tutorials. So without any further delay let us proceed with understanding in depth the properties of f divergences. So f divergence let us define it. So f divergence, the definition goes like this: given two probability distribution functions so we have been given distribution functions, okay, given probability distribution functions with the corresponding density functions. Okay. See, we have the distribution functions and then their corresponding density functions. So what are the distribution functions that we have? We call it PQ which we have, and then their corresponding density we represent it by small case P and Q. So now then the f divergence between them, the f divergence between these distribution functions between them is defined as df between the distributions p and q is integral over the support q of x f of px divided by qx dx. So qx which is the likelihood in terms of q and then the likelihood ratio which is there are considered here. Okay. So now again what are the properties? Now the f of u should be an r plus to r. Okay. When I say r plus I am assuming 0 is included here. So that is the what do you call assumption that we have 0 is there. Okay. So and then this function is convex and then it is left or lower semi continuous and f of 1 is 0. Okay. Under these assumptions, okay, now let us proceed. This is the definition of the f divergence. Okay. So now let us first take now f of 1 is equal to 0. Okay. Let us first take that into consideration. Okay. So now f of 1 is equal to 0. How, why is it needed? Let us look at now. Now assume p, the distribution function p is absolutely continuous to q, so that the likelihood ratio p of x divided by q of x is well defined. Okay. Is well defined whenever needed. Okay. So I am assuming that all of you are comfortable with these terms. So whenever needed. Okay. So now let us represent this likelihood ratio which is there. So, let us consider this likelihood ratio, let me call it as R of x is P of x divided by Q of x. Okay. Now, this is the likelihood ratio that we are considering. Now, then now we are already under the assumption that f is a convex function. Okay. So, f is convex function and we can use Jensen's inequality. Now, remember Jensen's inequality, we have defined Jensen's inequality in the review of probabilities. Please go and look at it, or another thing that you can look into is if you are not comfortable with the definition of convexity or Jensen's inequality, there is a very beautiful Wikipedia pages that are there on Jensen's inequality and then the proof for Jensen's inequality. In our earlier review of probability tutorials, we have only defined the Jensen's inequality, Markov inequality or Chebyshev inequality, we have just defined them. So, we have not looked at any of their proof, assuming that the viewers of these videos are equipped enough with those proofs. So, if not, so you can at least for Jensen's inequality there is a very beautiful Wikipedia page which is there. Now, please you can go and look at the proof over there, and then even for what is a convex function. So, if you have questions you can visit that Wikipedia page and clear yourselves the ideas. Okay. So, now we can use Jensen's inequality. Now, how then please be under please be very clear that the f-divergence that we have defined is actually an expectation. Okay. I presume that by the definition it is pretty much clear that the f-divergence that we have defined is a expectation with respect to q. Okay. So, I am assuming that, and then f is a convex. So, we can go ahead and use the Jensen's inequality definition. So, now because of that, how does the definition will turn out? See, the expectation with q, then you have this f of r, this is what we have. Now, because of the Jensen's inequality, it will be less than or equal to f of expectation with respect to q of r. So, why? Because we are assuming f is a convex function. So, this particular idea holds over there. So, now let us try to understand now what is this, let us try to evaluate what is this expectation of this likelihood ratio that we have. Okay. Now, what is this? Now, this is integral q of x into what is r p x divided by q x dx. Okay. So, now this will be integral p x dx. See, p x is a valid density function. So, therefore, its integral has to be 1. Now, because of which, now what will happen? This expectation of the likelihood ratio will become 1. So, now I think from here it is pretty much straightforward. So, now from here, so what is the f-divergence with respect to this? Now, this is expectation with respect to q of f of r, this is clear. Now, by Jensen's inequality, now this will be less than or equal to f of expectation of r, and this is equal to f of 1 from our earlier thing, and then so this will be 0. So, now because of the assumption that f of 1 has to be 0, see what happens is the divergence, the f divergence that we have will be always be greater than or equal to 0. Okay. This is the first part. Okay. The f divergence which is there is always the greater than or equal to 0, fine. So now let us proceed with the next one. The next question that we want to ask is, now when will be the divergence, when will be the divergence be 0? Under what conditions will this divergence be 0? Okay. So now under certain conditions, suppose the f which is there, the function that the f that we are considering is strictly convex, f is strictly convex again. So for the definition please visit, okay, strictly convex at u is equal to 1. Okay. Now then the equality in Jensen's inequality, see remember Jensen's inequality now has greater than or equal to symbol. Now I am asking when will be the equality holds is what I am looking into. Okay. So the equality in the Jensen's inequality occurs only when the random variable that we have under consideration now, which is r of x, okay, which is there, is constant with q almost surely. Okay. Only then this will hold. So now only in that cases now the f divergence between the distribution p and q, it will be 0. Now what does this mean? Okay. Now what do we mean by this? So that is, now when will be the r of x be constant? So let us assume that it is a constant and proceed, so that we will be able to understand with respect to that. Okay. So now this implies this implies the likelihood ratio p of x divided by q of x which is there is a constant, okay, is a constant for q almost surely. Now this should hold, but we already know that, from our earlier discussion, we already know that the expectation with respect to q of this likelihood ratio which is p of x by q of x that we have, now which we have represented by r, okay, p of x divided by q of x which is there is 1. Now this therefore c equal to 1. Now what do you mean by c is equal to 1? So that means that p of x divided by q of x is equal to 1, q almost surely so now what does this mean? So which means so p of x is equal to q of x almost everywhere. So now therefore the divergence between the distribution p and q will be 0 only when p is equal to q. Okay. Now we will be able to understand the two conditions that we have put for the f divergence. Now which are, now what were the condition if you remember, df between two distributions now has to be always greater than or equal to 0, and then df of two distributions is 0 only when they are identical. Okay. Now, we have looked at both of these properties, and then we have mathematically proved. So, when will these conditions holds? Okay. So, let us proceed. Now, this is regarding the conditions of the f divergence. So, now let us go to the couple of examples of f divergences. Now, let us look at examples of f divergences. Now, in our lecture, now sir has already described one f divergence which is there, which is the KL divergence. So, now let us start with that and then see. Okay. Now, notice the definition, again let us recall the definition. The divergence now between two distributions P and Q, now it is Q of x, f of the likelihood ratio P of x divided by Q of x dx. Okay. So, now let us change these f functions and see, let us use different f functions and see what are the different divergence that we get. This is the standard f divergence formula. Okay. This is a class of divergence matrix. Okay. So, now let us look at the first one, now which is the first one. Now, we choose here, in this case we choose f of u, where u being a dummy variable, u log u. Let us choose this as the f function and then see what will happen. So, in that case, so the divergence between P and Q is integral Q of x, this is there. Now, we want to replace f with u log u. Now, what is u? U is the likelihood ratio. So, now then what will happen, this is Px divided by Qx log of Px divided by Qx dx. Now I think the remaining things all of you are capable of simplifying. Px log Px divided by Qx dx, and this is now what is famously known as the KL divergence, okay, between P and Q. Okay. And I just want you to remember that what is the relationship between this and the MLE estimate that we have done earlier, okay, maximum likelihood estimation that we have done. Now, can we look at the maximum likelihood estimation as minimal KL divergence estimation? Please take it. Now, if you have taken any rigorous course in first entry level machine learning course, this should have been the first proof that you would have seen. Okay. So, now this is the first f divergence that we have considered. Now, let us consider another, the second choice for f divergence. Now, let us choose this f of u to be minus log u. Okay. This is what we have chosen. So, now then what will happen, the f divergence now between P and Q, now it is integral Q of x minus log of Px divided by Qx dx. Now, from here I assume that it is pretty much crystal clear, it is Q of x, use the properties of log Qx divided by Px, okay, dx. Now this is dkl between q and p, and this is what is famously known as the reverse KL divergence. Okay. See, the choice of the f is leading to us to different divergence measures. Okay. Now this is the reverse KL. Now let us take the next one. The next one that we take, let us choose f of u to be half into the absolute value of u minus 1. This is the choice of the f function that we are taking. Now then the f divergence is equal to integral of q of x half of px divided by qx minus 1 into dx. This is integral of q of x half px minus qx divided by px dx. Okay. Oh sorry, in the denominator there is qx, sorry it is not px, in the denominator it is qx. So now see, q is a density function. So and you know the properties of density function, now because of which I can write it as half px minus qx, okay, dx. Now this is what is the total variation distance between p and q. Now please remember I am using the term distance. I will justify the use of the term distance now maybe in the last part of the discussion of this tutorial. Now this is the total, this is the total variation distance. Okay. Now this is the choice that we have taken for the f function that led us to the total variation distance. Okay, fine. So now let us choose one more, the famous one which sometime down the line you will be seeing. Now let us choose the f of u to be half u log 2u divided by u plus 1 plus half log 2 divided by u plus 1. Okay. Now this is the choice of the f that we have. So now let us look at it now. Now the u which is there, now it is px by qx. Now let us take each of the term and then let us do it. First I will just look at the term. So this term now will be half px divided by qx into log of 2 times px divided by px plus qx. See, I think this is pretty much clear. Now you have u plus 1, now u is px by qx. So you qx, so it will be px plus qx divided by qx, and in the numerator also you have px by qx. So I have cancelled it. So I am assuming that these simple arithmetic operations you should be able to do it. Okay. So now then this is the first term. Now the second term now will be half log of 2 into qx divided by px plus qx. Okay. Now this is what it becomes. Now this is the f of u. Okay. So this is the f of u. So now and then you have a q of x outside. Now let us look at the divergence. So now df of pq, now this is integral q of x f of p of x divided by q of x, now dx. Now you can immediately see here that you have a qx here. Now once you replace this whole f of u here, there is a q of x that will go inside. Now therefore you can rewrite this whole thing into half integral of p of x log of p of x divided by p of x plus q of x by 2. Okay. This into dx, okay, plus again half q of x log of q of x divided by p of x plus q of x divided by 2. Now this is pretty much evident that now this is KL divergence between two distributions, this is pretty much evident. So this, if I represent this whole thing, let us say with some mx, if I represent these things with respect to some mx, so I can write it. So now this will become, let us say m is p plus q by 2, and then we can write the small mx which is px plus qx by 2, okay, while calculating the likelihood ratio. Now therefore, now what will this will be? Now this is half into integral of px log px by mx dx plus half, oh sorry, there has to be an integral here, maybe I missed an integral here, okay. So since I am writing it as two integrals, I missed an integral here. So integral of qx, and then there has to be a dx here, okay, qx log qx divided by mx dx, okay. Now this is half dkl between p and m plus half dkl between q and m. This is what is famously known as the Jensen-Shannon divergence between p and q, okay. Now if you remember, sir explicitly took this example. Now what is the difference now in terms of KL and reverse KL? Now what will happen and what points are given more weightage in KL divergence, what points are given more weightage in reverse KL, and then he explained that we need a combination of that, now which is nothing but Jensen-Shannon divergence. Now we explicitly took this example in the class. I hope you remember that, and then you would be able to understand it now with this in a much more clearer manner, okay. Now these are a couple of examples that we can look into. Now there are so as you remember, there was a very nice joke that was discussed that now we have A GAN, B GAN, so all the alphabet GANs are there. So the point that was made during that, which was emphasized during the lecture class also, now which is now change the f divergence. So you the f function, now you will have a different divergence measure which is there. Now because of which we get different classes of GANs that we get, okay. What is GAN we will look at it up sometime down the line. So now in the next part, now what I want to emphasize is we made a very interesting remark that the KL divergence which is there is not a distance metric. Now why did we make such a statement? What was the intention of that statement? Now what do you mean by a distance metric? What are the properties a distance metric should satisfy? Now let us look at it now. Okay. So now we discussed, so we made a statement that KL divergence is not distance metric. So let us see why. Now why is DKL not a distance metric? Is not a distance metric. Now let us look at it. Why is it so? See, any distance metric which is there has to satisfy 4 properties. Okay. Now we will define each of those 4 properties and then we will see that what properties are not satisfied by the KL divergence. That is what we shall do. Okay. So now a distance metric should satisfy 4 properties. So now let us take each of those properties and then we will see. Suppose the distance between 2 objects P and Q is d of P comma Q. Okay. Now then d of anything is a distance metric if and only if it satisfies these 4 properties. If it satisfies this property. Now among that let us take the first property now which is non-negativity. So what do you mean by non-negativity? So the distance between any 2 objects P and Q has to be greater than or equal to 0 always, and we have just in the earlier case we just proved it that the KL divergence satisfies this. So KL divergence satisfy this property. So now out of 4 property, 1 property is satisfied by KL divergence. Okay. So now let us take the second property which is there, the identity of indiscriminables. Now what do you mean by this? Now the distance, okay, sorry to use the distance metric between the objects is 0 if and only if these 2 objects are same. Now we already know this, now even the KL divergence satisfy this. Okay. So the DKL satisfies this. Now out of 4 properties, the 2 properties that we have seen, now both the 2 properties are satisfied by KL divergence. So now let us go to the third property. The third property now which is the property of symmetry. Now what do you mean by the property of symmetry? Now the distance between P and Q should be same as the distance between the objects Q and P. Does KL divergence satisfy this? Okay. This is not satisfied. Okay. We trivially know this from our earlier example. The forward KL and the reverse KL are two different things. Okay. KL divergence does not satisfy this. So we know this. So the DKL between P and Q is not same as the DKL between Q and P. Let us take a very simple numerical example to ensure this case. Now let us consider some Bernoulli distribution. Okay. Consider P which is 1, Q which is 0.5 and 0.5. See, these are masses. Okay. So I am reusing okay. So y, let me write it properly. Okay. So what is the issue with that? Let this be P and this is Q. Fine. So now then in this particular case, now what will be the DKL? The DKL will be the DKL between P and Q will be 0.9 log of 0.9 divided by 0.5 plus 0.1 log of 0.1 divided by 0.5. Now this is approximately 0.368. Okay. I am assuming that all of you are very much comfortable in doing this. Now then what is DKL of Q and P? Now this is, I have already computed this, is 0.511. Now this is straightforward simple numerical example to show that, see, the DKL of P and Q is not same as the DKL of Q and P. Okay. This is pretty much evident for us. So now why is this the reason? Now because of the overlapping points. So that happens, that was discussed earlier in the class. Okay. Let me just make a point. Okay. So now if you consider now the DKL between Q, now this is expectation with respect to P log of P by Q. Okay. I am abusing notations, I am assuming that all of you are able to understand my abuse. So what does this mean? Now this is regions where P is large matter a lot. So regions where P is small, see when I say P I mean so the likelihood that is being computed, okay, hardly matters. Okay. No, but what will happen when you take DKL between P and Q, what is that we are asking here? Now we are asking how surprised, now it is kind of average of that, okay, how surprised is the model about samples that actually occurs. Now on the other hand, if we take DKL between Q and P, now this is how much probability does the model assigns to regions where data rarely occurs. Now from this explanation it should be straightforward clear that now why do we need a combination of both forward KL and reverse KL. Okay. If we want to sample, now we want both of these things. Okay. So therefore we want a combination of this. Okay. Now how do you get this combination is by Jensen-Shannon divergence. Now what is Jensen-Shannon divergence equivalent to? Now hold on, now we will get to that in our discussions. Now therefore from the what do you call from understanding of these equations itself it is pretty much clear that these represents two different things. Now therefore by it is very natural that symmetry does not hold. Okay. Now this is one of the straightforward reasons why the KL divergence which we have is not a distance metric. Okay. Now see this is the third point which is symmetry, but if you remember it has to satisfy 4 points, no. Now what is the fourth point? Now that will be our next question. See the fourth point that needs to be looked into is the idea of triangular inequality. The fourth point is triangular inequality. Okay. See roughly what does triangular inequality means? See you want to so let us say that you want to go from P to R. Okay. So the distance that is there from directly from P to R, and then the distance that you take from P to Q and Q to R. Now the distance directly from P to R has to be lesser. Okay. So if you have a point P here, you have a point R here, and then you have a point Q here, that is why it is called as the triangular inequality. Now what is that being said here is the distance for P and R, oh sorry it has to be less than, sorry not greater. Okay. Yeah. So this is Jensen's inequalities prabhava. Okay. I am writing it the other way around. So it is less than P of Q plus distance between Q and R. Okay. So now let us look into it. Now what does this say? Now going directly from P to R can never be longer than going through Q. Okay. Now this is the idea of triangular inequality. Now let us see whether this is satisfied. Now let us take P, again some Bernoulli, okay, write it small p. Okay. Let us take P is 0.1, 0.9 and Q let me say 0.5, 0.5 and R which is 0.9, 0.1. Now what are the DKLs that we want to compute? Now DKL between P and R that is approximately 1.758. Now DKL between P and Q is approximately 0.368 and DKL between Q and R is approximately 0.879. Now from this it is directly clear that 1.758 now which is from P to R is greater than 0.368 plus 0.879 sorry 0. Okay, sorry I just sorry this is not 879, now this is 0.511, therefore whose sum will be 0.879. Okay, yeah, 0.879. Now this is violating the triangular inequality, so which violates the triangular inequality. Now therefore the KL which is there is not what do you call a valid distance metric. Okay. Now and one more thing is, you cannot have a kind of this geometrical interpretation for KL divergence, that is another reason. Now this is what we wanted to conclude. Now, I just want to give you a very small exercise. Now is total variation distance a valid distance metric? Is total variation distance, now which we have just looked at earlier, is it a valid distance metric? Okay. Now from the question itself it has to be clear, but what I want you to do is just go through all the 4 steps and compute the things and convince yourself, yes, total variation distance which is there is a valid distance metric. Okay. So with this we conclude today's discussion, so wherein which we understood the ideas, the properties of f divergence, and we understood them in mathematical terms, we proved all those things, and then we took couple of examples of KL divergence. Now by varying examples of f divergence, KL divergence was one. So we took different f functions, because of which led us to different divergence metrics like KL divergence, reverse KL, total variation distance, Jensen-Shannon divergence. So we came across these different divergence metrics, and then we understood why is KL divergence which is there is not a distance measure. Okay. So these are the things that we have looked at in this tutorial. I hope it was helpful and complementary to the points that were discussed in the lectures. Now we will look at the next section as we go along the weeks. Thank you all. I hope you enjoyed it. Meet you next time. Thank you.